Hello friends, my name is Pankaj Gupta. I manage the core data libraries team at Twitter. My team provides libraries like Hummingbird, Scalding, for processing any kind of data at Twitter, batch or real time. What I'm going to be talking about is an optimization we did for decoding Thrift objects better for certain use cases. And this is a use case that is very common at Twitter. I would imagine it's common in general. The way I'm going to be doing this presentation is that instead of talking immediately about what this optimization is, I want to provide some context. And then I will take a case study example and then walk through what the problem is and how AdaptiveScrooge solves it. So bear with me, I'll come to the actual implementation details, but in a while. So let's start from zero. What is Thrift, right? Most of you probably know it, but just to reiterate, it's an interface definition language. The idea is that you define your data schema once, and then you can generate code for it very easily in any of numerous programming languages. Why do you want to do that? Because it supports schema evolution. You can keep adding more fields to it. Old systems can read new data, new systems can read old data, all that stuff. The wire protocol is pretty efficient. You don't need to keep reinventing it. It provides language independence. Your different parts of infrastructure can work in different languages and talk to each other. For our purposes, it also supports efficient code generation. Because the code generation is automatic, over a period of time, we can keep evolving it and providing more options. And AdaptiveScrooge is another option that it provides you. So you just drop and replace and benefit from optimizations. And this is made possible because of code generation in Thrift. Second part is Scrooge. So what is Scrooge? Scrooge is a Thrift code generator. So Thrift comes with its own code generator, which generates Java code, which you can read from Scala, but it's not very idiomatic in the sense that it generates mutable objects, and as you know, in Scala we don't like mutability. So Scrooge is built for creating idiomatic Scala code. These objects are immutable, and also they make this nice design choice where your Thrift types are actually traits. They are not implementations like in the Java implementation. And what that allows is that you can change the underlying implementation of those types without changing any of the user code. So your application continues to run the same way. You can just plug in a different implementation. And that is what also makes AdaptiveScrooge possible. So what is the problem that we are trying to solve? The problem is that many jobs, they access very few fields, but they end up deserializing the entire payload. By job, I mean a real-time job or a Hadoop job or even a service, anything that is reading Thrift object. The way you would read is that you have a data source, and the data source is built for general usage, not just for your job, right? So it might have a lot of stuff, and usually you are interested in a subset of it. But you end up deserializing the entire object, and which in many cases might be more computation than you are actually doing. It might be the major portion of the computation that is happening. And I'll go over an example of that. So the typical way of, so this is a well-known problem that there are many jobs which want to access a subset of fields. And the typical solution has been to use a columnar format like Parquet or ORC. So what is a columnar format? In a columnar format, the data is stored by columns and not rows. What that translates to is that you have a stream of events, and each event's data is stored together, which is what we call row. So you have the bytes for the first event, then the bytes for the second event, and so on. This is the way data is regularly stored. In columnar format, you store data of together, not for the event, but for columns. So let's say your event had 5 fields in it. Let's say name, age, gender, blah, blah, blah. What you would do is that you would store data for a column together. For the name fields of all the events, they would be together as contiguous bytes, and then the other column, and so on and so forth. The advantage is that you can read the data for only the columns that you want. So if you are interested in name and age, you don't need to read all of the other columns, right? So this is a great, very good solution. So why not? Why is it not a good fit for all use cases? The reason is that there are some cases where it doesn't work yet, and in some cases it maybe theoretically can't work as well. The first case is real-time data. As far as I know, Kafka streams and not Kafka streams but Kafka and the other queuing implementation that we've seen, they give you event at a time, and they don't support projection push down right into the stream. You still have to read the data event at a time. So you don't benefit from columnar formats there. Even for batch data, we've seen in practice that if you have a lot of columns, then this breaks down. For example, if you have a schema where it has hundreds of columns, it's actually faster to read it row by row than reading it column by column, because every column adds an overhead. For a few columns, like 4 or 5, it doesn't matter. But as you go into hundreds of columns, the overhead actually kills performance. So in those cases, practically, we still don't use Parquet. So there are actually a lot of data which doesn't use a columnar format. You could say that you could have data in both formats, right? And depending upon your use case, you use this data or that. But storage is a huge cost. Doubling the storage is also very, very expensive. So in the end, you end up with one format. And then you end up in a situation where you're back to square one, you have a large object, you only want to access a few fields. And that's the use case that AdaptiveScrooge addresses. So as I promised, let's start with an example. This is a very simple application, event in, event out. Let's say your services are generating events, and somehow it goes to a demaxer, right? It could be that you're writing to some log categories that through Scribe or Flume, it goes into HDFS. Then there is a demaxer which does categorization, right? You categorize this event into separate horizontal categories. This is a practical use case which we have for some jobs. And let's look at this event here. So this is a typical event where, let's say there is a type field which is an integer. This is all you need for categorizing this data. What category does this data go into is dependent upon only this field. But there is all the other data in the event. Like there could be an expensive string, there could be a huge map, a set, and it could have nested event structure, which is very typical at Twitter. Like we have like 10 levels of nesting. See? So in this, you just keep in mind that we only need the type field here, which is integer. Now let's go inside the demaxer. What happens? You get this event, which in raw bytes form. Then you deserialize it, which means that you create object in JVM memory, which has the map materialized, the set materialized, all the nested structures in there, all depths, as well as the type field. So you deserialize it in this in memory. You take up a lot of memory. You do a lot of work for deserialization, and then you check the type field and categorize it. After categorizing it, you write it to different categories. It could be different Kafka streams or different locations on HDFS. For serialization, you take this materialized event in memory and then convert it into bytes. Now you can see the actual logic that you're applying is very tiny. It's like almost nothing. You're checking a field called type and deciding category. But all the other work that you're doing is so much more expensive. Materializing this stuff in memory, and then your GC can go up because of that, and serializing it back again. Typically, for such a system, you would actually write custom code, right? Because this is like a very, very specific example where this problem blows out of proportion. I chose it because it shows this use case very, very well. But typically, when you're working on this project, you would say like, let's put the bytes with the object. Let's not deserialize it again. You write a lot of custom code that you have to write, test, maintain, all of that. If you don't do that, then you pay the price. So those are the options. Now let's see how AdaptiveScrooge solves it, and then we'll look at how it works internally. So at the top level, what AdaptiveScrooge does is that it learns from the access pattern. It learns from your executing code and sees what fields you are accessing. And it figures out that type is the only field that you're accessing. And then it deserializes only the type field. It skips all the rest. When you read the bytes, it would skip everything else as fast as it can. The code is optimized for that. And it materializes only the type field. And it also changes the representation of the event. It completely gets rid of the fields that you don't need. So in your memory, you're not creating the map, the SAT, the nested structure. All of that is gone. And then after you categorize it, and you want to send it to different categories, serialization is just copy. You take the original bytes and just copy that over. You already had the bytes, right? You got the bytes already, so it's not any additional memory allocation. It's just a simple copy, which is a very, very fast operation. So overall, you're back to or close to your actual logic and avoid this overhead. That is the use case for AdaptiveScrooge. Now let me go over the details of AdaptiveScrooge one more time. So it learns from the access pattern. It's similar to just-in-time compilation in Java. Like in JIT, you look at what portions of code are accessed, and you optimize those code to run with native. This is a similar idea. We learn from which fields you are accessing, and it modifies your code to be optimized for that use case. In this case, only the type field is materialized. We don't materialize rest of the field. It does carry around the original bytes, but those were already allocated, so it's not a new memory allocation. There is an implication to carrying it around, and we'll look at some of the downsides. It saves memory usage because you're materializing very tiny objects, the part that you're accessing. You avoid all the rest. Reserialization is free, not just for the actual object, but even if you were projecting and looking at a nested field inside, any level of nesting, it would basically copy the portion from the original byte array that you need. So it's still a copy, even for projections. It eliminates entire nested structures, and it is a drop-in replacement. It's very simple to replace it. Your code does not need to change at all. With that in mind, it would be not fair to omit lazy Scrooge here. Lazy Scrooge was the step that we had before we went to AdaptiveScrooge. This is not a completely new idea. This already existed for a long time, and we've benefited a lot from it in practice. It gets us halfway there. What it does is that it makes the strings lazy. And as it turned out, for a lot of our Hadoop jobs, just decoding the string was very expensive. And lazy Scrooge made that lazy. So only if you access that string, it would decode that string from bytes. So it was a step in the right direction. It also avoided reserialization. So it also carries around the original bytes. So if you want to reserialize it, then it's just a copy. So it solves those two problems, but it does not solve the maps and sets case. Those are still materialized, and sometimes those can be expensive. And it still goes through all the nested structures. So only the strings are lazy. Still has to, even if you're not accessing the entire big nested structure, it still has to go. But it was a good first step that led to AdaptiveScrooge. So let's go deeper into how AdaptiveScrooge works. As I said earlier, it learns from field accesses at runtime and learns and adapts based upon this information. So first part of AdaptiveScrooge is, which I call learning, is that we wrap the original Thrift object. So whatever the default Thrift representation is, we generate code using that, and we wrap that in a wrapper where whenever you access a field, it updates some counter somewhere. And you can specify this learning period for how many events you want to do that. So in this first process, let's say you say 10,000 events. For those events, it would, through this wrapper, learn what fields are getting accessed. And at the end of it, it does the adaptation. So what it does is that it modifies the decoding code where you are converting bytes into an object representation, and it generates optimized code which skips the bytes as quickly as possible. There are like zero allocations there. It just like reads through the bytes to get to the next thing that you need, and very quickly, cheaply skips data. And second thing is that it does is that it also creates a different implementation for your Thrift object, the one that does not at all have the fields that you don't access. So in this case, this adapted event only has the field that you access. And this decoder generates that representation of the object, right? So pretty simple at the top level. You're rewriting the decoding code as well as the representation of the object that you materialize in memory. For the user code, it's the same interface. It continues to work the same way. The way adaptation is done is via bytecode manipulation. We take the actual generated code at runtime. We use ASM to manipulate the bytecode. We put hooks in the original bytecode so that at runtime we can modify the bytecode and load the modified bytecode for that class at runtime using a class loader. So why did we choose ASM? We did not actually start with ASM. We started by generating the code as a string at runtime, then using Scala compiler libraries at runtime to load this code. You can do that, right? It was very, very slow. It would take like 3 to 4 seconds for the big thrift structures that we have at Twitter. And some of our MapReduce jobs, they run for only like 30 seconds. So this is a huge overhead. Like 10% of the time, it's not viable at all. And Scala compiler is a huge dependency. Like some of these services, they are in Java. They don't even depend upon Scala. Now there is another thing that they need to depend upon. ASM, so we tried ASM then and like focused on optimizing this, and ASM works pretty well. We were able to bring this time down to 100 milliseconds. And this is for a very, very large thrift. But typically it would be like order of a few milliseconds. So that was a huge improvement, and now it's viable. Like even for a 30-second map job, this is like a third of a percentage. It's like basically noise. So that becomes viable then. Even this 100 millisecond pause though could be problematic for some services. They can't afford to have performance go down even for 100 milliseconds. So this transformation happens in the background, and then it's applied atomically. So there is no pause in the application when you use this. Another advantage of ASM is that it's a tiny library. It doesn't depend upon many other libraries. It's like pretty simple library, and it's a very lean dependency. So when you bring in ASM, you're not bringing like a whole bunch of libraries with it. At Twitter, we depend upon Finagle a lot. Most of the applications do, and Finagle already depends upon ASM. So for us, it's like zero. There is no additional cost to depending upon ASM. But even for outside, like if you are using Scrooge, this is a very tiny dependency that you need to add. So one aspect of AdaptiveScrooge is fallback. So you did this learning. What if you learned wrong, right? Somehow for the first 1,000 events, this field did not get accessed, but later on it got accessed. So in that case, because it has the original bytes, it's able to fall back. It will go back and deserialize the bytes again, and then you work around that. So your application will work correctly. You're not tied into that the learning has to be correct. It will still work correctly. And the fact that you did not see these accesses in the first 1,000 or whatever you configure events means that this is like a rare event. And in that case, if you pay like 20-30% extra performance, that's fine. And you can tune also like how long you learn. Second fallback is that if we realize that all fields are accessed, then we fall back to the original thrift, because the whole point of AdaptiveScrooge is that it's optimized for a subset of field accesses, and we don't want to add any penalty if you're accessing all the fields in the object. And there are actually cases where it's very common to access all the fields. For example, if you are partitioning events, grouping it, and you need to do a hash code of the event, the hash code actually goes through all the fields, right? Or if you're converting the data from one format to other, let's say you're converting from Thrift to Parquet, you actually have to go through the entire event. So there are actually practical cases where you end up accessing all the fields, and there you don't have to pay any price. It will learn and then fall back to regular Thrift. There are a couple of tuning parameters. You can train for how long. So for example, batch jobs, they hardly ever change in the access pattern. So you can have a small portion of reads there. For a service that is running for days, you have more flexibility. You can train for longer. You can also decide at what percentage access does a field get materialized. It may actually be reasonable to not materialize a field that is accessed rarely. So like I said, that if that field is indeed accessed, we'll fall back to the original Thrift and we can decode it. There is some performance penalty to it. You can compare that to the cost of deserializing that every single time. So for example, if a field is getting accessed 2 times out of 10,000, you might want to like ignore it. Don't deserialize it in the regular case, and as and when it is accessed, deserialize it. So those are the parameters that you could tune. Typically, you don't need to tune that much. So as we know in software, there are trade-offs. There are very rarely complete wins. There are some trade-offs with AdaptiveScrooge as well. So it does not account for changes in access pattern. So if your application is running for days and days and now the access pattern changes, it doesn't know. It did the training and now it doesn't know. And we could fix that, but we haven't seen a good use case for that. Typically, services get deployed pretty frequently, and the code is pretty representative of what fields you access and such. It could be built, but we haven't built it yet. Second downside is that the nested structures, they all access the entire Thrift blob, right? So if you have a nested structure and there is a tiny nested struct inside that you're caching in memory, it will actually with itself store the entire byte array, which could be problematic for caching, right? You don't want to carry around the whole byte array. In that case, you could clone the object. So there is a little bit of work required in this edge case. This I talked about already, that if you do a hash code right now, it would materialize all the fields and AdaptiveScrooge is defeated. But this need not be the case. We'll probably optimize it in future. For calculating the hash code, you don't need to materialize the object. We could infer that from bytes itself. Another downside is that the jars are a bit bigger because now we generate more code. So your bundle that you deploy could be a bit bigger. Depending upon what portion of your application is generated code, this may or may not be an issue for you. There are some wild cases we've seen where this might matter. Using it is pretty simple. Basically, ultimately, this boils down to converting bytes to types. You provide your settings, you create a deserializer, and then you can get your type from bytes. So pretty simple. These are the results. So we built a benchmark for it, which is part of the open source repo. You can run it if you want. And this benchmark is built to show the utility of AdaptiveScrooge. So take it with a pinch of salt. But in this case, there is a big schema. Very few fields are accessed. It's actually 20 times faster than regular Scrooge and 10 times faster than lazy Scrooge. But this is built for the case fit for it. We also saw 10% improvement in real job, a production job that runs, and which was actually a candidate we thought was fit for this optimization. There we saw 10% improvement. We ran another benchmark with not just the deserialization part, but actual real-time topology. So this is a real-time topology running on Heron with a simple map and sum by key, which is counting events basically. And in this case, the spout is where most of the deserialization happens, right? And we saw 25% reduction in CPU usage on the spout. So this is not a real job, again, because this is a benchmark. It has to be repeatable. So there are some differences. And it's also built to show the utility of AdaptiveScrooge. So coming back, like, is it better than Parquet-ORC? No. If you can use columnar formats, it is they are better because they do less file I/O, they do less network reads, and less decompression. The data is typically decompressed on HDFS from where we read it. But for the cases where it doesn't work, which are very real at Twitter, for that use case, AdaptiveScrooge is optimized and built. In conclusion, you can deserialize only what you need. It's possible. Thank you.